Okay, here, now we know how to find the derivatives now of logarithmic functions. Now what we want to do is find their antiderivatives. As a reminder, we found that the derivative of the logarithm of x is the reciprocal of x. And by the chain rule, the extension of that is the reciprocal of the argument times the derivative of the argument. And I'm going to consolidate that just in the interest of space. Okay. Now, again, this I think is going to be key for us when we're doing antiderivatives. Look at that last expression. Okay. Notice that in the denominator, you have the function g of x. And in the numerator, you have exactly its derivative. Okay. Anytime you see an expression that looks like that, where the numerator is the derivative of the denominator, you know that you're looking at the result of the derivative of a logarithm, excuse me. Okay. Okay. So let's just jump right in. Example. I suppose I wanted to find the antiderivative or the integral of the cotangent of x dx, right? Well, you may not know that. You could look it up at a table, I guess, but that's no fun. Where's the romance in that? Instead, I think what we'll do is, let's rewrite it. Cotangent is the cosine divided by the sine. Okay? Notice in the numerator, the sine of x is exactly the derivative of the denominator. And so when you go back and look at this later, you know what we were thinking. I'm going to write it like that. Okay, so now that we see it for what it is, gang, what is that? Right, remember now, the integrand is the derivative of some function. What function? Good, the logarithm of the sine function. Oops, not 6, but sine. Gang, I think what I'm going to do, I think this is a good place to remind you that you can't take the logarithm of negative numbers or 0, okay? So typically what we do when we're solving problems like this, we put absolute value bars around the argument just to be sure. And this is okay, right? All of us know that the sine function takes on positive values and negative values depending on what quadrant you're in, right? So in order to be careful, it's best to put absolute value bars around the argument of your logarithm. Okay, how about this? What do you think? Do we have that, for lack of better words, do we have a log rule, do you think? Yeah, gang, if you think about it, what is the derivative of the denominator, 4 plus x? It's 1, and you have that in the numerator. And to emphasize that, I'm just going to rewrite. Now, you don't have to keep doing this. I just want to illustrate the point, okay? That the numerator is exactly the derivative of the denominator. And anytime you have that, you know that you're looking at the result, taking the derivative of a logarithm. And so in this case, it's going to be the logarithm of 4 plus x. All right, how about this? All right, now look, gang, you've got an exponential function in the top and the bottom. It's 3 to the x. It's not the natural logarithmic function, okay? Let me remind you from a previous lecture. Okay, where our base, the letter a, would take the place of the number 3. Now, is our numerator exactly the derivative of the denominator? Because if it is, then we've got that logarithm thing. No, you're good. It's not exactly the same, is it? In fact, we're off by a little bit. We're off by a logarithm, right? We're off by a constant, and that constant is the logarithm of 3. I'm going to fix that. Okay, so I multiplied by a clever expression of 1, didn't I? Now the numerator is exactly the derivative of the denominator. Let me rewrite again. So when we go back and look at this later, we know what we were thinking. Okay, so the top is exactly the derivative of the bottom. We know we have exactly this expression right here. That's what we're going for. And so we'll then have the natural logarithm of the quantity of 5 plus 3 to the x. In this case, gang, it may interest you to know that the expression or the argument 5 plus 3 to the x is positive no matter what you do. And so in this case, to have the absolute value bars around it is really kind of redundant, right? Having absolute value bars around something that's already positive doesn't make it more positive. So you can actually use parentheses instead. Yeah, that's a simple enough one, huh? Very good, very good. I'll use absolute value bars to be careful, like we had mentioned before. And here's an interesting remark, gang, I think you'll appreciate, okay? Now we know that this is true, that the derivative of the logarithm, the natural logarithm of x, is 1 over x. Okay, we know that. I'm getting sloppy. Okay, now for this one, I'm going to need the chain rule. Okay, right? There's a composition. You don't have just x in there, you've got negative x. So by the chain rule, the derivative of the logarithm of negative x is the reciprocal of negative x. Okay, times the derivative of negative x, which is just negative 1. Okay, but notice that the 1 over x, which is the reciprocal function, that's the same as this right here. So in other words, that's equal to how about that? So the derivative of the logarithm of x is the same as the derivative of the logarithm of negative x. Well, here's a little bit more. If your interest is piqued, and I hope that it is, here's something more. You're going to love this. From the old days, our Algebra 2 pre-calculus days. The definition of the absolute value of x, remember this, gang? The absolute value of x is equal to x if x is already positive or equal to 0. Otherwise, it's the opposite of x if x is a negative number. Right, that's the very algebraic definition that is, right? We know the geometric definition, right, from our earliest days back in pre-algebra. Oh my gosh, even for you young people, that's going back, right? Absolute value means distance from the origin. So if I say, what's the distance between 0 and 8, you would say 8, or just the absolute value of 8 equals 8, right? But negative 8 in terms of distance is also 8 units away. Well, the opposite of negative 8 is positive 8. Okay, because again, notice here's the important thing. Notice that both of these here and here show up here and here. So what we can do is we can actually consolidate both of those two derivative formulas and write like this. The derivative of the logarithm of the absolute value of x is equal to 1 over x. Because no matter which expression for the absolute value of x you use, positive x here or negative x here, you're going to get the same result, okay? And by the chain rule, this implies that the derivative of the logarithm of the absolute value of any function is equal to the reciprocal of that function times the derivative of that function. So here's the big takeaway, gang. When you take the derivative of the logarithm of a function and you have the presence of absolute value bars, it's as if they're not even there when you take the derivative, okay? You can totally disregard the absolute value bars in a logarithm when you take its derivative, okay? We just proved it. I've gotta love that. Okay, so here, the derivative of the logarithm of the cosine plus the sine is the reciprocal of the cosine plus the sine times the derivative of the cosine plus the sine. Okay, and I totally disregarded the absolute value bars as I took the derivative. Okay, you can always do that. Okay. Now here we have an antiderivative, right? We want to find the integral of the logarithm of x raised to the second power. And then we've got this x in the denominator. Gang, I'm going to rearrange the factors. Okay, see what I did there? Now the reason that I did this is so that you could see, right? So the x in the denominator, I just moved it over, so that you could see that the outside function 1 over x is exactly the derivative of the inside function raised to a power. That's our thing. That's the special case of the chain rule. And we can go right to the answer. Okay, and of course you can have absolute value bars around the x. Okay, now coming off that last example, you can probably see what's going on here. I'm going to move that x in the denominator over again. So that you could see that the 1 over x is exactly the derivative of the angle of the sine. This is a chain rule. Once again, it's a nice chain rule. It's not our thing, right? It's not the special case, but that's okay. The outside is the derivative of the inside. And so we know, based on our experiences, we don't need use substitution for this, just our experiences. Okay, and of course, I encourage you to check your answers by differentiating the result, as always.